Let me welcome you to this lecture. Now, in the last lecture, we have learned what is a mathematical group and essentially the rules which must be satisfied for a collection of elements to be called a mathematical group. Now, the reason why we are interested in mathematical group while dealing with symmetry is because the collection of symmetry operations in a molecule constitute a mathematical group also, or if you take all the symmetry operations in a molecule, then they are going to satisfy all the four rules of mathematical group, and this has a lot of important consequences in chemistry, and that is why we are interested in group theory while dealing with symmetry. Now, in this lecture, what we will try to demonstrate that how one can find out that if whether the collection of symmetry operations in a molecule is going to form a mathematical group, or we'll try to see if all the four mathematical rules are satisfied by the collection of symmetry operations in a molecule. And for this purpose, what we will do is that we will take the water molecule as the example, and so the symmetry operations in water molecule, as you can all of you can easily figure out, the first symmetry operation is identity operation generated by the identity element which is present in all molecules. Then apart from this, we have a C2 axis of symmetry that passes through the oxygen atom. Through this axis, if we do 180-degree rotation, then we will have a indistinguishable configuration, and the C2 axis of symmetry produces only one symmetry operation, that is the C2 operation, as the C2 is going to be equal to identity. Now, apart from this C2 axis of symmetry, there are two planes of symmetry. One is the molecular plane of symmetry, that contains all atoms of water molecule, which lies on the plane of this board. Now, if we take this as the z-axis, which contains the proper axis of highest order, that is the C2 axis, and as this as the x-axis and the y-axis as perpendicular to the plane of the board, then this plane of symmetry which bisects the oxygen atom, this will be the sigma yz plane, and the molecular plane which contains all atoms of water molecule is going to be the sigma xz plane. So these are the two symmetry planes in water molecule. Just to distinguish between them, we have denoted them as sigma yz plane and sigma xz plane. Now, before we go and find whether these set of symmetry operations satisfy the four rules of mathematical group or not, what we will do is that we will write the group multiplication table by using these four symmetry operations. So let us write the group multiplication table for water molecule. So we have the identity C2, sigma yz and sigma xz. So this particular mathematical group, which is formed by these four symmetry operations, it is known as C2V group, and also it is you may already have heard that these such notations, they are called point groups essentially, because here we consider the atoms as points, but we will discuss this in a later lecture, and for the timing we just denote this group as C2V point group, and let us write the group multiplication table for this point group. So we can easily write some of the products of the symmetry operations, because product of identity operation with any operation is going to give that operation itself. Product of E with C2 will be C2, sigma with sigma yz, it is going to give sigma yz, and with sigma xz is going to give sigma xz. Similarly, C2 into E is going to be C2, this is going to be sigma yz, and this is going to be sigma xz. Now, what we do not know are the product of this C2 with C2. Of course, this can be easily found by using mathematics, that we know when we do C2 operation 2 times, we should go to the identical configuration. So we should get the identity operation when we multiply C2 with C2. But just to prove our point, what we will do is that we will do C2 operation 2 times, and then we will see if we get back to the identical configuration or not, or whether the multiplication of C2 with C2 gives us identity or not. So let us do C2 once here, and I have labeled the hydrogen atoms now, so that we can distinguish between different configurations. So once you do 180-degree rotation with respect to this axis, H1 will move to the position of H2, while H2 will go to the position of H1. And then if we do C2 once again, what you will see, you are back to the configuration where you started. So this particular configuration and this configuration is exactly same, they are identical. That means when we do C2 2 times, we get to the identical configuration, or the multiplication of C2 with C2 will give us identity. So we can write C2 with C2 as identity. Similarly, we know sigma yz with sigma yz is going to be equal to identity. That also we have discussed. And sigma xz with sigma xz will also be equal to identity. So we now have to find out these two product, as well as this one over here, this one here, and the product of sigma yz with sigma xz. That also we can do in the same way. We can figure out what is the result of these products. So let us now begin with the first one, maybe C2 with sigma yz. So let us do C2. This is going to be 2 and this is going to be 1. Then let us do sigma yz. Our reference axis should be there, otherwise we may confuse between different reference planes, and that is the reason why we should have this the reference frame here. So when we do sigma yz, that is, we will be bisecting the molecule in this way using that molecular plane, and H2 will go to H1 will go this side again, H1 and H2. So this is, you may say that this is, we are going to the identical situation over here as we have done here, and we can write identity over here because we are getting the identical configuration. But if we write identity over here, then the group multiplication table is going to be wrong, as you can see, as per the rearrangement theorem, because identity operation here, if we write, then identity will appear 2 times in this row, as well as it will appear 2 times in this column. So this result of C2 with sigma yz is not actually identity, but if you see carefully, if we do sigma xz, that is, if we do reflection on sigma xz plane, with again the position of these atoms are not going to change, because simply that is the molecular plane and it contains all the atoms. So the result of C2 with sigma yz, we should write it as sigma xz, because that also gives us, this gives us sigma yz, also gives us this configuration starting from the initial configuration straight away. So then sigma C2 sigma xz, we can again find out what it is, sigma xz. If we do, that is, if we do sigma xz is the molecular plane. So if we do so, we will get so these atoms are not going to move their positions if we do sigma xz, and then they are going to remain as such. It will be this configuration. So this we can get this configuration, we can get straight away by doing sigma yz. So that is why we can write sigma yz. Also, what we should notice that all the symmetry operations appear at least once in the group multiplication table. Only then it is going to be correct. This is true for this particular row, as well as this is true for the second row also. We see that all the symmetry operations of C2B point group are there, but they are there in a rearranged way now. So then let us proceed with this group multiplication table, and then let us try to figure out what is the product of sigma yz with C2. So sigma yz with C2. So if we do sigma yz here, so that is this, bisecting a molecule or doing reflection with the perpendicular plane here, then again we will have the same configuration here. H2 will move to this side and H1 will come to this side. So I don't have to rewrite this part. And then we'll have to do, because we want to find out the product of sigma yz with C2. So let us do C2 now with respect to this, the C2 axis of symmetry which passes through the oxygen atom. So if I do 180 degree rotation, what I will get is H1 and H2 like this. So again, this configuration we get by doing sigma xz. So we can write sigma xz here, sigma xz. Then sigma yz with sigma xz. We see sigma yz with sigma xz. Sigma xz, what we will get is, because sigma xz does not change the position of the atoms, they will remain as such, and this should be equal to this configuration we can get from here straight away by doing C2. So the product of sigma yz with sigma xz will be equal to C2. Again we can see that as per the rearrangement theorem, all the symmetry operations appear only once in this row as well. Then we have to find out the product of sigma xz with C2. This is going to be, when we do sigma xz, atoms do not change position, and then I have to do C2 operation here. If we do so, this is going to be H2, this is going to be H1, which is sigma yz. So we can write sigma yz here. Again you can see it is possible to now complete the group multiplication table without doing any further verification or doing the symmetry operations in successive ways, because we know as per rearrangement theorem here, in this particular column only one element has not, or symmetry operation has not appeared so far, that is the C2 operation we can write, but we will of course verify whether we can write like this or not, because at times you may think that this is going to give us wrong answer, or when you have a large group multiplication table, or if you have a large number of symmetry operation in a point group, then it may be difficult to write the products in this way by guessing, and then instead doing the multiplication or doing the symmetry operations successive ways is a more accurate way of completing the group multiplication table. So we will verify if this is correct, if the product of sigma xz with sigma is equal to C2 or not. So here we will have to do sigma yz. So if we do sigma yz, that is the plane which bisects the molecule here, so then again we will have this. So this is, we see from here to here, you can get straight away by doing C2 operation. So the product of sigma xz with sigma yz is equal to C2 in fact. So this completes the group multiplication table for the C2B point group constituted by the symmetry operations of water molecule. Now what we will see if all the rules of mathematical group are satisfied here or not. So the first rule says that the product of all the symmetry operations or the square of any two symmetry operation should be an element of the group itself. So it is obvious from the group multiplication table here, because what we have done here, we have multiplied all the symmetry operations with each other, as well as we have done the square. We have also got the answer of the square of each of the symmetry operations. So for example, we have found out what is the product of multiplication of C2 with C2, sigma yz with sigma yz itself, sigma xz with sigma xz itself. And what we have found that all the products as well as all the squares are symmetry operations, are results, or are symmetry operations which belong to, which appear in C2B point groups. That is, the result of multiplications are either E, C2, sigma yz or sigma xz, which are elements of the group. So rule number 1 is satisfied by this combination of symmetry operation. The second rule says that there must be an element which commutes with all elements of the group and also leave them unchanged. That is the identity element which is present in any molecule, because we can say that an operation was like rotation through an axis by an angle of 360 degree is an identity operation. Also doing no movement at all is also an operation that is called the identity operation. So the identity operation is present in all molecules, and that is why the second rule of mathematical group is also satisfied, because the product of identity operation with any other symmetry operation will give us that operation as well, and also the multiplication of identity with any symmetry operation, it follows, they commute with each other and they follow the commutative rule of multiplication essentially. So the second rule is also satisfied by the symmetry operations of water molecule. The third rule says that multiplication should follow the associative law of multiplication here, which is correct. Again, you can verify whether if you do so whether associative law of multiplication is followed or not. We just try to find out whether with this example whether both sides, left hand side and right hand side, gives us the same answer or not. So when we do C2 with sigma xz, what we get, C2 with sigma xz, what we get is sigma yz, and then we have sigma yz here from here. So on the right hand side, what we have is C2 sigma xz sigma yz. So sigma xz with sigma yz gives us C2 again. So the result of this is sigma yz, answer is identity, and this side C2 with C2, this answer is identity. So what we have proved from here that we have randomly chosen a product of three elements here, and what we have found is that the associative law of multiplication holds good in case of this group, or in case of this collection of symmetry operations. The fourth rule states that we have to find out whether the fourth rule of mathematical group is followed by this collection of symmetry operations in water molecule. The fourth rule essentially states that there must be a reciprocal for each of the element, and the reciprocal, whenever we multiply the element with its reciprocal, then what happens is that we will get the answer as identity. So we'll see what are the reciprocals of these elements. The reciprocal of identity is identity itself, because when we multiply identity with identity we get the answer identity. So the reciprocal of identity is identity itself. Now the reciprocal of C2 we have to find out. So we'll find out on multiplication of C2 with which other element gives us identity operation. So in this case what we see again, multiplication of C2 with C2 gives us identity. So C2 itself is the inverse or reciprocal of the symmetry operation C2. Now again, the reciprocal of sigma yz is sigma yz itself in this case, and in this case reciprocal of sigma xz is sigma xz itself. Again, as because when we multiply sigma xz with sigma xz, then we get the answer identity. So in this case especially, each element is its own inverse. In case of the C2 point group, what we have seen that each of these elements reciprocal is the element itself. Of course, this may not be true for other point groups or other symmetry operations, and because at times we see that there are other symmetry operations which are reciprocal of the elements. So for example, in case of, if we want to find out what is the reciprocal of these C31 symmetry operation present in, say, ammonia molecule, you will find when you multiply C3 with C32, then you get the answer identity, because when you do C3 one times and then if you do C3 two times here, then the total is going to be C33, and that is why the answer is going to be identity operation. And in this case, the inverse or reciprocal of C31 operation is actually C32 operation, and similarly reciprocal of C32 is C31 operation. So the reciprocal may not be the same symmetry operation, it may be different symmetry operation as well. Only in case of C2b point group, what we see is that the element is its own reciprocal. So what we have essentially seen in this case is that the symmetry operations of C2b point group, there are four symmetry operations: identity, C2, sigma yz, and sigma xz. These symmetry operations follow all the four rules of mathematical group, and that is why this collection of symmetry elements can be called a mathematical group. And of course, it is, we call this particular group is the notation to denote this this particular group is C2V. That is, we call it point group because here we again we consider the atoms to be points essentially, and that is why it's called point group. So with this, we'll conclude this lecture. We will learn more about mathematical groups in the next lecture.